Okay, so I'd like to start off with this quote. A language that doesn't affect the way you think about programming is not worth knowing. How many of us have dismissed CSS because it's just a markup language, it's not JavaScript, but I would like to argue it does affect the way we think, whether it's like cuss words that we say to ourselves because we just get irritated with it. I think it's worth knowing. As she said, I used to be a former figure skater. I work for a company called Built Technologies. When I worked on this talk, I was working for Warner Brothers, so that's a big portion of why I did this talk. I do a podcast called JavaScript Jabber. I'm a panelist on that. I used to do Angular Air. I am a big runner, and I spend a lot of time in the gym. So why am I talking about CSS to a room full of JavaScript developers and Angular developers? Well, first, I want to start off a little bit and talk about my story and why I did this talk. Like I said, I worked for Warner Brothers for a while, and when you work for a company like Warner Brothers or Disney or something like that, their design is everything. It's their brand. So before I worked at Warner Brothers, I just spent most of my time focusing on JavaScript because that's what really mattered, the functionality. But when you work for a company like that, when you're off by a pixel, it matters. And I got really frustrated because I was able to debug my JavaScript really well, debug my Angular code really well, but a lot of times I felt like I was just like blindly throwing darts at a dartboard when I was trying to debug my CSS, and I just got really frustrated. Also, I think knowledge of internals are really helpful for advanced debugging and performance tuning. So, we all like to make sure the JavaScript in our applications are performant, but not a lot of us spend a lot of time focused on our styles. And then also, in the future, we're going to be able to modify the browser's rendering engine. There's a task force coming out, something called Houdini, and what they're doing is they're working different people from different browser vendors, and they're coming together to expose a set of APIs so we can hook into the rendering engine ourselves. So this is a really popular question that a lot of people ask, why can't I just use component-based styling? Won't this solve all my problems? So component-based styling is going to help you get around a lot of specificity issues, but at the same time, you're going to lose the cascade, which is a key component to cascading style sheets to CSS. So imagine if you do have component-based styling and you don't have any global variables and you have to go into every single component and update a variable when you want to change the color, that would be really painful. So CSS is not JavaScript, so we have to think about it a little bit differently. So what I'm going to go over today, I'm going to start off and go into some browser internals and how the browser is actually parsing your HTML and your style sheets. Then we're going to go a little bit deeper into the parsing process. And then before we close out, I'm going to talk about the most problematic areas I see people are having issues with, so that would be specificity, positioning, and z-index. I'm going to talk about how you can debug these and some common problems that I see people hitting. So let's dig into some browser internals here. So we're going to go over this rendering engine main flow. I'm going to start with the DOM and how that's actually constructed. So first things first, when the browser goes and fetches your HTML sheet, it's not actually fetching what we think of as HTML. It's fetching just raw bytes off of the network. That process is called conversion. Then the browser is going to translate those raw bytes into individual character codes based on the file. So it knows that it's parsing a HTML sheet, and it knows that it has to translate those characters accordingly. Next, it takes those characters and it turns them into tokens via the tokenizer. What the tokenizer does is it's just breaking up that input into valid tokens, so we can kind of think of it as forming an abstract syntax tree or an AST in JavaScript. It's something very similar. So it's going to break things up into, you're going to have like your start tags, end tags, your attributes, and your values, and the tokenizer is going to strip irrelevant characters. So for HTML, white space would be irrelevant, and line breaks. It's going to look something like this. Next, it takes those characters and it's going to turn them into individual nodes. Finally, those nodes are, the parser is going to analyze the document structure according to the language grammar, so it knows that it's parsing HTML. And we're ultimately going to be able to construct the DOM. But a note about the DOM. So the DOM is what we call not context-free. So it's a little bit different than JavaScript and CSS. So with the DOM, as we all know, we can give it ill-formed HTML, and it's going to render it no matter what. So when the browser is parsing your HTML, it has to take into account the surrounding characters to the individual node it's on. It needs to know what comes before and what comes after, because sometimes if you're missing something, the browser has code within it. It has to be smart enough to go ahead and like close a tag if you forgot to close a tag. So I like to think of it this way. When the browser is going and parsing through your HTML, it's a very clunky process if you give it stuff that is ill-formed. It's not a conventional parser. Unlike CSS, like I try to be when I'm skating, it should be a very smooth process. Same thing with your JavaScript, because it's a conventional parser. It doesn't have to account for all these strange edge cases. Okay, so that probably might have been review for some people, but now we're going to get into the CSS Object Model. And if you're anything like me, before I started doing this talk, I had never heard of the CSS Object Model before. So who in here has heard of the CSS Object Model? A couple hands, not very many people. Okay, hopefully I can help you guys out then. So to the browser, the DOM and the CSS Object Model are two completely different data structures. But again, the CSS Object Model, we can think of it like an AST, like we do with JavaScript. It's a very similar structure to the DOM. So like HTML, the browser is going to need to convert those CSS rules. So it's just getting raw bytes off the network again into something it can understand. It needs to convert those raw bytes into actual CSS. So we're going to repeat pretty much the same process we did with our HTML for our CSS, but I'm going to note a couple differences. So the CSS Object Model is not one-to-one with the DOM. So the DOM is going to capture properties and relationships to the markup, but it doesn't actually tell us how the entire page should look when it's rendered to the screen. So another important thing to note here, by default, now you can change this based on different attributes that you add to things, but by default, CSS is treated as a render blocking resource. So if you want your sites to be performant, you have to understand that until the CSS Object Model is constructed, you cannot execute your JavaScript. Because if we tried to go ahead, if the browser tried to go ahead and execute the JavaScript, a lot of times our JavaScript is reaching for things inside of the DOM, inside of our CSS, and if we haven't completed that yet, the browser could get wrong answers. It could also be very jarring to the user, because if we think of CSS, it has a cascade. So if something higher up paints the screen red, and then we fall down into the cascade and it paints it blue, that would be really jarring for the users. So the CSS Object Model, like I said, is not one-to-one with the DOM. So things like script tags or meta tags or head element, basically anything that's not reflected in the rendered output is not going to be in the CSS Object Model. Next up, though, we have the render tree. So the render tree is a tree of visual elements in the order in which they're to be displayed, because a lot of times our CSS is going to reorder things. So that's why we have to have the DOM. Or I'm sorry, that's why we have to have the render tree. So the render tree is just a mashup of the CSS Object Model and the DOM. It's a visual representation of the document, and it's going to enable painting in the contents in their correct order, because like I said, the DOM is not going to be the final order. And if we think about it, the CSS Object Model can have drastic effects on the render tree, but it has zero effect on the DOM. So each node in the DOM tree that has visual output is going to have something called a render object in the render tree. And each render object is going to know how to paint and lay out itself and its children, so this is a recursive process. And each of those render objects, they're going to include geometric information like their width, their height, and their position. So let's try to visualize how this render tree is actually constructed. So we're going to start at the root of the DOM tree, and we're going to traverse each node. We're going to omit the non-visible nodes, because those don't matter. And then for each visible node, we find the appropriate matching CSS Object Model rule, and we're going to apply that to the render object. We're going to omit then the visible nodes with their content. So we have our HTML and our text, and then our computed styles. And then finally, we output this render tree that contains all of those render objects with all of their visible content. Okay. So now that we've done this deep dive into the browser internals, let's go into the rendering phases. So we can think about it, the browser really is broken up. When it's trying to render things, we can think of it broken up into 3 different phases. We have layout, paint, and composite. And this is where, when you're applying your CSS rules, this is where the different rules come in. So again, like I said, I wanted to be able to debug my CSS just like I did my JavaScript. And sure enough, I can go into the Performance tab, and I can debug the layout from there. Layout, depending on what browser you're looking at and which actual browser code, it's often called reflow. And layout, what layout is responsible for is the position and size of each of those render objects. And the output of the layout process is a box model that's going to contain the position and size of every element that you see on the page. After layout, we run paint. Again, you can inspect that in the Performance tab. Paint is often called raster sizing, and it's converting each of the nodes in those render tree into the actual pixels you see on the screen. I want to call out this, though. So as we're trying to tune the performance of our style sheets, we want to pay close attention to painting time, because that's the most expensive part of these 3 processes. Obviously, this makes sense. The bigger the width and height of an element, the longer it's going to take to paint it. Adding different effects is going to increase your painting time. I also want to call out this. So I find that a lot of JavaScript developers or Angular developers, are super excited about keeping up with our programming skills, our JavaScript skills, our Angular skills. But when it comes to CSS, we're kind of like, ugh, I don't really want to. I love Flexbox from a usability standpoint, but if you're trying to make your apps performant, I thought this was really interesting. So somebody took a floated layout, they converted it to Flexbox, and you can see how much more performant it was. So if we're trying to debug things and we're trying to understand the cascade better, it's important to understand painting order. So painting order follows the order of elements as they are in their stacking context, which I'm going to get into when we get into the z-index section. And it can be global or incremental. So what I mean by incremental, the browser is smart enough to know that only certain areas of the page need to be repainted. So it's going to generate It's going to generate a paint event just for that specific dirty region. So as you can see here, I'm hovering over this Grownups tab, and as I hover over, I change the styles. But if you inspect in the developer tools, you can see that the paint event is only getting triggered for that button. Finally, we run Composite, which again, you have to actually go in and enable the Layers tab, but you can inspect that as well. But what is compositing? So it's rendering different elements of a web page in layers. And when a lot of people like to talk about hardware acceleration, that's what compositing is. Compositing hooks into the GPU rather than the CPU. So let's go over this stuff really quick. So adding a DOM node is going to cause a relayout and repaint of the parent node. Increasing the font size of the HTML element is going to cause a repaint and relayout of the entire tree, so that's going to be really expensive. Changes to an element's color is only going to repaint. We don't need to do a relayout. Transform and opacity, if you can, those are the ones that you want to reach for. So if you're trying to hide something on the page, reach for opacity, because opacity is just going to trigger a composite. We don't have to run a relayout and a repaint for that. And then layout always triggers paint. Just keep that in mind, because changing the geometry of an element means the pixels need to be resized. OK, so let's get practical. So I have this little quiz here. We're not going to spend a lot of time on it since this is a short talk, but I have this small section of markup and then the associated styles, and I want people in their heads to guess what color the anchor tag is going to be. And the answer is pink. So I find not a lot of people usually get this right. And how did we come up with pink, though? Let's actually do the calculation. So the answer there is 111. But again, we can think of it as 111, but we have to understand that those commas are there to remind us that it's not a base 10 system. We could have something that starts with a 0, or we could have like a 13 that's not going to spill over like a base 10 system. But we can think about it in our heads when we're calculating it up like that. So if you're trying to debug, you don't understand why a specific style is getting applied, it's important to understand specificity here. So the first column, we're going to count up the number of style attributes. So in this case, we didn't have any. The second column, we're going to count up the number of ID selectors, and those are going to give us 100 points each. The third column, we're going to count up the number of class selectors, attribute selectors, and pseudo-classes, and those are going to give us 10 points each. And then the final column, we're going to count up the number of type selectors and pseudo-elements, and those are going to give us 1 point each. So that is why, if we look at the second row, we have a 3 in that last column, but because they only count for 1 point, that is why that one didn't win. Okay, so positioning and layout. So these two go hand in hand, so we're going to go back to layout a little bit that I talked about earlier. Layout is a recursive process, but width and height are computed a little bit differently, and I see people getting tripped up about this a lot. I myself was one of those people. So width is calculated just based on the current render object, but height is a little bit different. So for the height, for each child, the current render object is going to determine the position of the child, and then it asks the child to compute its dimensions, then the current render object can compute its height based on the children. Finally, z-index. This is probably my favorite one. It appears so simple that I find a lot of developers don't really dig much deeper into it, but it can get tricky. I've seen this happen to really, really, really advanced developers. So the key to debugging debugging z-index is to understand what a stacking context is. It's a three-dimensional representation of the HTML elements along a z-axis, so facing the user. And it's just a group of elements that move backwards and forwards together. So to the browser, we have either a root stacking context or a local stacking context. The root stacking context is just going to be from the DOM itself. And then the local stacking context, that comes into play when we apply certain properties and values like z-index. Within a local stacking context, the z-index values are all relative to the root, rather than to the document root. And then if we think about it, layers outside of our particular stacking context we're in, so sibling elements of a local stacking context, they can't sit between layers within a different context. So it's all about understanding which stacking context you're in, because you can't affect the siblings of that one. So stacking context rules. This makes perfect sense. Higher values are placed in front of lower values. We all know that. That's why we give something a really high z-index and hope that it will move to the front. But when we apply auto, or when things have the same value, then we just go off of their appearance in the DOM or in their HTML. And then people who maybe don't have a strong computer science background, we have 2,147,483,647. So that is a maximum signed value of a 32-bit integer. So if you try to apply a z-index value of something higher than that, the browser literally will not let you, because it's limited by the programming language that the browser is actually written in. But I have a huge surprise, and this is where z-index gets super complicated. So z-index isn't the only way to create a stacking context. There are other properties that will create a stacking context. So a lot of times, if you're trying to increase your z-index value and you find that it's not working, you might want to look at some of the other rules that you've applied to that specific element. So opacity, when its value is less than 1, so if we're trying to hide something on the page with opacity, that's going to create a new stacking context. Filter, when its value is anything besides none. Mix blend mode, and then applying transforms. Those are all going to create new stacking contexts. So this is probably the #1 thing I see really, really, really advanced UI developers getting tripped up on in CSS. I've seen teams spend weeks actually trying to debug this. So finally, I want to leave you guys with this. I think computers are really good at following our instructions, but not at reading our minds. So when we sit back and we think about it, I would hope that today I have tried to enlighten you guys on CSS and convinced you that you can actually debug your CSS just like you do your Angular code, just like you do your JavaScript code. Thank you guys so much.